Good day, class. In the past lectures, we have finished combing through the derivatives of different classes of functions, namely the algebraic, circular, logarithmic, exponential, inverse circular, hyperbolic, and the inverse hyperbolic functions. Today, we will be discussing the relationship of properties of the derivative f prime with the original function f, and thus giving us some great results on applications of the derivative. In particular, in this video, we will first learn the main tool in proving these results, namely the mean value theorem. Now, without further ado, let us begin. We will first prove a theorem made by Rolle, which is a simpler version of the mean value theorem and can be used to prove the mean value theorem. Let us state Rolle's theorem. If I have two real numbers a, b, with a less than b, and I have a function that is continuous on the closed and bounded interval ab, and differentiable on the open and bounded interval ab, and that the evaluation of my function at a and b are both 0, then what happens? Well, Rolle noticed that under these assumptions, firstly, f of a equal to f of b equal to 0 mean that the graph y equal to f of x will intersect the x-axis exactly at a and at x equal to b. Continuity and differentiability mean that you have a smooth continuous curve from the point a f of a and b f of b. And Rolle noticed that if you're under these assumptions, there will be a c such that the derivative at c is 0, or that the tangent line at the point c will be a horizontal tangent line. This is a very important theorem. Of course, we need to satisfy these three main assumptions so that we can have the following conclusion. If any of these are not satisfied, then we are not certain that the conclusion will occur. For example, in the case that continuity and differentiability are not satisfied, then we are not sure if the graph will have a horizontal tangent line, which is given by the next two examples. For example, this one is not continuous at b, and clearly, even though f of a is equal to f of b is equal to 0, you will not have any horizontal tangent line along any point in the middle of a and b. So we don't have continuity here, and for this, we don't have differentiability at this point. And even though you are only not differentiable at a single point, you will not be able to find any horizontal tangent line in any point between a and b. So you will see how important it is that we have continuity and differentiability so that we can readily conclude that we have a horizontal tangent line. But please be clear, even though continuity and differentiability are important, if you are not continuous and you are not differentiable, it does not mean that you do not have a horizontal tangent line. Discontinuity and non-differentiability only imply that you do not have any conclusion. Again, if you are discontinuous or not differentiable, then it just means that you are not certain what the conclusion may be. For example, this is a discontinuous function, and you don't have a conclusion, you don't have a horizontal tangent line. But for this example, you are also not continuous at a, but you will still have a horizontal tangent line. So the main idea here is the assertiveness or your certainty that you will have a horizontal tangent line. If you are continuous, differentiable, and the evaluations are 0, then you are assured. So that's the word, you are assured of a horizontal tangent line. If any of those three assumptions are not satisfied, the only thing that you can conclude is that you do not have any conclusion. Now for a final remark, do know that Rolle's theorem is an existence theorem, very similar to the intermediate value theorem, and that is, the c exists, but you don't know where it is, and you don't know how many there are. For example, this case where you have f of a is equal to f of b and they're both equal to 0, you are just sure that there is at least one that will have a horizontal tangent line. In this case, it will have two, but you don't know what that is, and we were only able to know because we graphed it. So Rolle's theorem will not tell you the value of c. The only properties of c that you know are: 1, it is between a and b, and number 2, its evaluation at the derivative will be 0. Now let's have an example. I want to determine if Rolle's theorem applies to this function. Essentially, the example asks us if we know the three main assumptions or conditions so that we can apply Rolle's theorem. And those are continuity, differentiability, and that the evaluation at the endpoints of my interval will be 0. Let's check. Well, how do we check continuity and differentiability anyway? Continuity, we have done that before. For example, since this function f is a polynomial, then it is easily concluded that you are continuous and differentiable. Continuity follows from the theorems that we had in the first unit. Differentiability follows from the fact that the derivative of a polynomial is also a polynomial, and as long as the derivative exists, then you are differentiable. So you get continuity by taking note of the results in the first unit, while you get differentiability by differentiating this, getting a polynomial, and saying that it exists everywhere, in particular from 1 to 2. Also, if you evaluate f at 1 and 2, it is easy to see that 1 minus 4 plus 5 minus 2 will be 0, and 8 minus 16 plus 10 minus 2 will also be 0. That means that Rolle's theorem can be applied and there is an interior point C such that f prime of C is equal to 0. In particular, we can even solve for this C. The derivative is just 3x squared minus 8x plus 5, whose factors are just 3x minus 5 and x minus 1. And clearly, x equal to 5/3, which is the 0 for this, will be between 1 and 2. We are not going to be considering x equal to 1, as we only will be considering C from 1 to 2. So we want it to be open at 1 and 2. Remember, we are continuous on the closed, differentiable on the open, and our conclusion is also on the open interval. Let's have another example. I have this piecewise function and I want to show if Rolle's theorem applies to it. Again, we have continuity, differentiability, and the evaluation. Let's check first for continuity. So clearly, from 0 to 1, the function x squared and x minus 1 will always be continuous. The problem is what will happen on the boundary value 1/2. And if you evaluate f at 1/2, that is evaluation at x squared, that is of 1/4. Get the limit of f of x as x approaches 1/2 from the left, that is also 1/4. However, when you evaluate f of x as x approaches 1/2 from the right, that will become the limit of x minus 1 as x approaches 1/2 from the right, and that's a negative 1/2. What does this mean? It means that your function is not continuous or discontinuous at 1/2, and that means Rolle's theorem cannot be applied. Again, we did not say that we do not have a horizontal tangent line. The only thing that you can conclude when you are discontinuous or non-differentiable is that we cannot apply Rolle's theorem. And that is for Rolle's theorem. Using Rolle's theorem, we can prove mean value theorem. It will not be shown here, but it can easily be read in the literature, and I suggest that you read on it for completeness. Let us now state our main theorem of the day. If I have two real numbers a, b such that a is less than b, and my function f is continuous on the closed and bounded interval ab, and differentiable on the open and bounded interval ab, and that's it. So unlike Rolle's theorem, where we still have the third condition that the evaluation of f at a and at b are both 0, mean value theorem is much simpler because it only needs continuity on the closed and differentiability on the open intervals. The conclusion will be as follows. There will exist a c in AB such that the derivative of f at c is equal to f of b minus f of a over b minus a. A little bit more complicated than Rolle's theorem because the derivative just becomes 0. But what does the right hand side mean? Though it is kind of complicated and you have evaluations of f, do know that this is a constant with respect to x. Remember that a and b are already given in the first problem. It's like saying I consider the interval 1 to 2 or 4 to 16. So f of b is just an evaluation of a constant, another evaluation of a constant, over a difference of two constants. So this is a constant. It gives you a slope. And the slope is what? The slope is essentially the slope of what we call a secant line. It's the line connecting a f of a and b f of b, which is easily computed as f of b minus f of a, the change in y, over b minus a, the change in x. And mean value theorem states that there is a c such that the tangent line at this point c is parallel to the secant line. So it's still a condition on the tangent line, and a very, very interesting application for this will be that when you have the derivative at c, it is in a single equality as your quotient difference. Always remember this. As much as we want to connect the properties of f and f prime, the problem is the original relationship of the two is divided by a limit. Remember, f prime of x is equal to the limit of f of x minus f prime of x naught is equal to the limit of f of x minus f of x naught over x minus x naught as x approaches x naught. So there is this limit in the middle, and because of that we can't really do any algebraic relationship between the two. But mean value theorem states that because of this result, I can somewhat connect in a single equality a derivative and the evaluation of f, and thus will give birth to properties of f prime influencing a property of f. Now unfortunately, we do not have that much time to see the applications of the mean value theorem, and we will be satisfied in understanding whether we know when and when we cannot apply the mean value theorem. For example, I have f of x equal to x plus 2 over x plus 1, and I need to show that there is a c such that f prime of c is equal to negative 1 over 6. One of the greatest problems when applying mean value theorem is that the conclusion is normally kind of complicated. As if I go back, since this is a complicated quantity where I still need to evaluate at f at b and f at a, subtract and then divide, we will see here that at first glance, how are you going to show that it is equal to negative 1 over 6? Unfortunately, the only way that we can do that is to try a lot of examples. For example, in this function f, I will first ask, is my function continuous on the closed and bounded interval 1, 2? Now this is a rational quantity, and we know that a rational function will only be discontinuous when the denominator is 0. And that's at negative 1. Since negative 1 is not in this interval, then you are continuous. Differentiability is also obtained by just differentiating this, and you will see that the denominator will just be x plus 1 squared from quotient rule, low d high minus high d low over low squared. So that means it will not be differentiable as well when x is equal to negative 1, and that is still not part here. If you're going to do this in your exercises, exams, and quizzes, I suggest that you write down your whole reason why you can say that my function is continuous or differentiable, saying continuous because f because negative 1 is not part of my interval, and differentiable since f prime is equal to this quantity and negative 1 is also not part of your interval. Now, unlike Rolle's theorem, we don't need the evaluation assumption here, and we can already go to the conclusion, which is there is a c in between 1 and 2 such that the derivative of f at c is equal to the difference quotient f of 2 minus f of 1 over 2 minus 1. As I've said, we need to somewhat simplify this so that we can see what f of 2 minus f of 1 over 2 minus 1 is. And if you compute for it, 2 minus 1 is just 1, f of 2 will be 4/3, f of 1 will be 3/2, and by subtracting this, you obtain the result, which is negative 1/6. What will happen if you did not get negative 1/6 here? Then what you do is you consider an interval smaller than 1, 2 in still a subset of 1, 2 such that you will obtain the negative 1/6. And that's how you apply this. Let's have another example. Now this is a very nice example as it gives rise to an application, truly an application of mean value theorem. Suppose I have a continuous function on the interval 6, 15 and differentiable on 6, 15. Notice I do not know the function f. Unlike in the previous examples where we already know what the function is, in here we only assume that f is continuous and differentiable. This is not an absurd assumption. As you may know, when you go to your workplaces after you graduate, it's almost impossible that you mine functions and then it will just blurt out inside your notebooks. What you normally have are studies, data sets, and you're going to assume continuity and differentiability on these functions even though you don't know its exact functional value. But at least what this example is saying is that on the assumption that you are continuous and differentiable and that the slope of the tangent line will never exceed 10. So that means you were able to notice that on your data set, all the tangent line will never have a very big slope. What you can conclude is this. If f of 6 is equal to negative 2, we can somewhat estimate the value at 15. So even though you don't know what the function f is, you can somewhat evaluate how big or how worse can f of 15 be. Now how does this work? Well, number one, because of the continuity and differentiability assumption, even though I don't know f of x, I know that the derivative of f at c will be equal to f of 15 minus f of 6 over 15 minus 6. And that is just equal to the following. Since I know that f of 6 is negative 2, I'll have plus 2 here, and 15 minus 6 is just 9. Now remember, we already have this assumption that you will not have a tangent line whose slope will exceed 10. What does that mean? It means that if you try to solve for f of 15, this quantity f prime of c will never exceed 10, or that is less than or equal to 9 times 10 minus 2. And that means 9 times 10 is 90 minus 2. F of 15 will not exceed 88. True enough, this is not an equality, but at least we had an upper bound estimate for your function, and sometimes that is enough for our studies. You will see here that mean value theorem is very much useful when you really don't know your function f. Of course, if you already know your function f, maybe it is better to just graph it or to try to solve the equation. But in cases that you don't know your function f, which is most of the time when you are applying it in real life problems, at least we have some results like this bounding result we have here. And that is it for mean value theorem. In the next video, we are going to be studying some results that is birthed from the mean value theorem, and that is in finding relative extrema and finding when a function is increasing or decreasing. Now I hope you have learned well in this video. Stay safe and thank you for watching.